Let's do some problems on quotients and homomorphisms and so on. So recall, so problem 1. So recall the following definition. M, an R module, is said to be cyclic. So we call M a cyclic module if it is generated by a single element. So there exists a single X in M such that M is just the submodule generated by X. Okay, in other words, it's all multiples of X, scalar multiples of X. Rx are coming from R. So if this happens, then we call M cyclic or singly generated. Okay, so here's the question problem. Prove that a cyclic R module is isomorphic to a special module R mod I, the quotient module R mod I, where I is a left ideal, where I is some left ideal. Okay, let's prove this proof. So firstly, let's ensure we understand the definitions here. Recall that if you have a left ideal of R, then you can think of it. So firstly, R can be thought of as a left module over itself. How is this? By sort of left multiplication. In other words, I take a scalar R in R. I think of the module also as being R itself. So let's suppose I have X in R. Then how does R act on X? Well, the scalar multiplication is just the usual multiplication in the ring R. Okay, so R is a left module over itself, and what are the submodules for this module? They are exactly what we call the left ideals. So the submodules of R under the left action are just the left ideals. Okay, left ideals just mean they are a additive subgroup, and if you multiply them on the left by any element of the ring, then it still belongs to the same left ideal. Okay, submodules are the same as left ideals, and what we therefore can do, you have a module R, you have a submodule which is a left ideal, and you can therefore take their quotient. So what's being asked to prove is that if I take every possible left ideal of R, consider the quotient R mod I, this collection exhausts the possible cyclic R modules up to isomorphism. Okay, every cyclic R module is isomorphic to a module of the form R mod I. So let's prove this. So what did we say a cyclic module was? So the best way to prove this really is to set up a homomorphism. So what do we have? We have a module M which is known to be cyclic, which means there is a single generator X. Okay, now let's do the following. Let's define a map from R to M. Let's call this map phi. What does this map do? To each element R of the ring, it associates the element Rx. Okay, so recall X is the fixed generator of M. So define this map R going to Rx. So the first thing to observe is that this map is actually so both sides R and M are R modules. This is a module homomorphism. This is a homomorphism of R modules. Okay, let's verify the properties. We need to check on the one hand that if I take a sum of two elements on the left, well, what does that give me? It is R plus X times X. But the fact that M is an R module means I have this distributive property, it's Rx plus Sx, and therefore that is just phi R plus phi S. Okay, so that's one. We need to check that if I take phi of, so I take an element of R and multiply it on the left by something, right? So I need to now take, let's give this a name. So I take an element R of the ring, and suppose I multiply it on the left by R dash. Okay, so I want this answer to be, so let's write down what we want. This is the second property of being a module homomorphism, that if I hit a module element on the left by r dash, the r dash should be, I should be able to pull it out. Okay, I want this to be true for all r dash in r. Okay, this is slightly confusing because the ring is also a module now in this case over itself, but you should convince yourself that this is exactly the second axiom of a homomorphism. Okay, now let's check that this is true. So phi of r dash r, so let's compute the left hand side. So what is this? By definition, this is r dash r acting on x. Now let's do the right hand side. This is r dash acting on phi of r is rx. Okay, but observe that these two are actually equal to each other because of the module axiom, because M is a R module, because M is an R module. So the R module axiom says when I have a product of two scalars r prime and r, when that acts on an element of the module, I can think of it as two repeated actions. Right? First apply the first scalar, then apply the second scalar. Okay, so what we actually have is that this map phi that we have defined is a homomorphism. Okay, now what else can we conclude about this? So first property of phi is a R module homomorphism. Second property, phi is on 2. Why is that? Because M was given to be cyclic. We were given this property, right, that every element of M is of the form r times x for some r. X is the fixed element, remember. Okay, so the fact that, so this is since M is cyclic. Okay, so now we are in good shape because we can sort of apply the first isomorphism theorem, which says that when I have a homomorphism, then R modulo the kernel of this map is isomorphic to the image of this map. Okay, now in this case, what's the image? The image is M, and let's call the kernel as I. So what is the kernel in general? Remember, if I have a homomorphism between two modules, the kernel is always a submodule. Okay, so let's call this fellow is I. So let I be the kernel of this map. Then that's no, we already know it's a submodule of R, but submodule, remember, it's the same as left ideal. Okay, so it says R modulo the kernel is actually isomorphic to M, and that's exactly what we needed to prove. Okay, so we just had to realize that submodules are the same as left ideals, i.e. Left ideal. I is a left ideal. Okay, in fact, this ideal we've actually proved a little more. We've said what was I, so we said R mod I is isomorphic to M, where I is exactly the kernel of the map. The kernel of what map? The map which sends each element R to Rx. Okay, so which means what? This is exactly the set of all R in R such that Rx is 0, right? And this is usually, this has a name, this is usually called the annihilator in R of X. Okay, it's all elements, all scalars which annihilate that element X. So R modulo the annihilator of X is isomorphic to Rx. So this is sometimes another form in which you will see this. R modulo the annihilator is isomorphic to the submodule generated by that element X. Okay, so all this, this is assuming that X is inside some module. In this case, we have assumed that Rx itself is M. Okay, so let's move on to the second problem. So again is about quotients and submodules. In fact, it's about submodules of quotients. So here's the problem, broadly speaking. So suppose I have a module M is an R module. Again, R is not necessarily commutative, and suppose I have a submodule N sub of M. Okay, so recall, that means that I have the quotient m mod n, and in fact I have a quotient map from m to m mod n. Okay, so this double arrow just means that this map is surjection, it's a surjection. So what does this map do? It takes each element x of m and maps it to the coset x plus n. Okay, so this is the this map is it's an R module homomorphism. It's a surjection. Pi is an R module homomorphism. Pi is onto. Okay, sometimes called the quotient map. Okay, so the problem is the following: determine what the submodules of m mod n look like. Okay, so prove that the submodules of this module m mod n are in one-to-one correspondence. They are in bijection. Show that there is a bijection between the submodules of m mod n and the submodules of m which contain n. Okay, so sometimes it's nice to draw a picture. So I have m, the ambient module, I have n, the submodule, and what we are saying here is that to understand the quotient m mod n, or understand the submodules of the quotient, it is the same as understanding what are the submodules of m which lie between m and n. So these p's, there could be several of them, these different submodules which lie between m and n, to each of them there corresponds a submodule of m mod n. Okay, so this is an equivalent way of thinking about submodules of the quotient. Okay, so let's just set up the bijection itself. So proving it is easy. So let me just tell you what the bijection is here. So here's the bijection. So on one side, let's write down the submodules of m mod n, and on the other side, let's take the collection of all submodules of m which contain n. Okay, so I want to establish a bijection between these two. So I'll give you maps in both directions. So here's the first thing. Suppose I have a submodule. So let's go in the forward direction. If I have a submodule of m modulo n, then here's what I can do. So for the moment just go back to the quotient map. So the quotient map is a map from m to m mod n. So what I could do is the following. So let's just move this. Okay, let's move this down. Now look at the submodule here. So let's take, so suppose I have a submodule of m mod n. Okay, so that's something which lives on this side. B is a sub of m by n. Now what I can do is I have this map pi. I can look at its inverse image under pi. Okay, inverse image just means, I mean, pi is not a one-to-one onto, I mean, it's an onto map, not a one-to-one map. But inverse image just means I take all the elements. So if B looks like this, okay, here's the ambient module m by n. Here's the ambient module m. The inverse image of B just means I take all elements of M which map to B, right? The pre-images of all elements of B. So that's going to be my map. So this pre-image is what's usually denoted as pi inverse B. So to each B, let's associate. So if this is my B, then to B I associate its inverse image under the projection map. Okay, by which I mean take all elements of M such that pi of x belongs to B. Okay, it's easy to check that this is a submodule of M, and it contains n necessarily, because observe that B is a submodule of M mod n, so B must have the 0 element of M mod n. Okay. So the first observation to make here is that this map is well defined. So let's just record this somewhere. So observe the inverse image of B is a submodule of M. That's easy to check. I believe that for you to verify. But the key property that we need is because B contains the 0 element, the pre-image of the 0 element, which is, well, what's the pre-image of the 0 element? It's all elements of M whose cosets give you the 0 coset, and that's of course n by definition. Okay, so the inverse image of the 0 coset is n, so n is certainly contained in every pi inverse B. So therefore pi inverse B is a submodule of M which contains n. That bit is fine. So now let's define a map in the other direction. So suppose I give you a submodule P of M which contains n, then this map is just pi of P. So I just map this to all the cosets. So I take P and I just map it to its image under pi, by which I mean all cosets okay. So these are the two maps, and I claim that these two maps are inverses of each other, that they give you the bijection that you want. Okay, or equivalently you could say that you can take any one of the two maps, let's say the red map, and show that it is a 1-to-1 and onto. Okay, so I mean the verification itself is very easy, and I hope you can do it. So let me just do one of them. So let's check, for example, that the red map is 1-to-1. So I claim that. So I mean, here's one way of proceeding. You prove that this red map is both 1-to-1 and onto. Show both its properties. So let's check that this map is 1-to-1 or onto, whichever is. So let me do one of them. Let me show it's 1-to-1. Maybe you can show it's onto. Okay, so to show it's 1-to-1, what do we need? I need to take two different elements, B1 and B2, two submodules of M mod n, and show if they are distinct. I need to show that their images are distinct. So if take two fellows, B1 and B2, so let's write it like this. I take B1 and B2, which are two different submodules of M mod n, and then I claim that their images are also distinct. So look at pi inverse B1, pi inverse B2. The claim is that pi inverse B1 is also not the same as pi inverse B2, and in fact this is just a trivial fact about, I mean, we don't really need the fact that pi is a homomorphism or anything. It's just a fact about set maps between sets. So let me just give you a diagrammatic argument. So if M and M mod n, I have a projection map pi which is onto, right? The key point is that pi is an onto map, and what I'm doing is taking two different subsets here. I mean, they are submodules, but let's just say they are subsets for now. So let's just use two different colors. So here are two different submodules, B1 and B2. Okay, so here's B1, here's B2, and I claim that if B1 and B2 are not equal to each other, then their inverse images, their under pi inverse, can't be equal. Okay, why is that? Well, observe that I'm given B1 not equal to B2 means either there is an element in B1 which is not in B2, or there is an element in B2 which is not in B1. So let's assume one of them. So this means that B1 minus B2 is not empty, or B2 minus B1 is not empty. Okay, so let's assume it's a former, say the first one. So let's pick an element x which is in B1 minus B2. Okay, so maybe not to confuse with the earlier x and so on, let me call it z. So z is actually a coset in this example because it's an element of M mod n. So let's take z in B1 minus B2 and observe that, so if z is here, because pi is onto, so I know that z must have some pre-image, right? So let's call this pre-image something. So let's look at, there's an element x of m which must map to z. Okay, so since pi is on 2, there exists an element x in m such that pi of x maps to z. Now observe that this x is certainly in pi inverse of b1 because it's the inverse image of an element z in b1, but it's not in pi inverse b2. But x is not in pi inverse b2 because what's the definition of pi inverse b2? It's all elements of m which map to some element of b2, right? But in this case x is not, x maps to z and z is not in b2. Okay, so this shows that pi inverse b, we have produced an element in pi inverse b1 which is not in pi inverse b2. So actually observe, for this we didn't really use anything about modules and so on. This is a general fact about onto maps between two sets and their inverse images. Okay, so this is the first part. The other part which I leave you to check, so I've checked pi is 1 to 1, check that pi is onto. Okay, again a straightforward verification. So the result is worth remembering, which finally says that submodules of a quotient are really nothing but submodules of m which contain n, okay, which lie between m and n in some sense. Okay, now let's do one last problem which sort of uses this submodules of a quotient business. So here's a so let me take a specific module. So suppose I have z modulo some power of a prime. So consider the following: z modulo the ideal generated by a single element p power n, and what is n here? Well, n is at least 1, p is a prime. So this is an ideal, so of course it's a left ideal as well if you wish, and therefore a submodule of z. Okay, so think of this as a z module. Z mod p to the n is a z module. Okay, the claim is that prove that z mod p to the n cannot be written as the direct sum, as the internal direct sum if you wish of two submodules, of two non-zero submodules. So everything here is a submodule, module over z, so two non-zero z submodules. Okay, so in some sense it says you cannot split it into the direct sum of two submodules, okay, with both non-zero. So let's prove this. So first observation is that what we are dealing with is really a quotient module. It's z modulo something. So it fits into the framework of the previous problem. So let's call this m, let's call this n. They are both z modules. N is a submodule of m. And what we are trying to do is to understand whether we can decompose this guy into a direct sum of two submodules, right? I want to see whether I can do this or not. Okay, to do this I need to understand what are the possible submodules b1 and b2, right? What do submodules of my quotient look like? If I can figure that out first, then I can then try and prove that you can never decompose in this way. So the first step is to understand the submodules of m mod n, and recall by the previous problem we know what submodules of m mod n look like. Submodules of m mod n are really in bijection. You can think of them as being in bijection with submodules of m. Okay, m in this case is z containing n, and n in this case is the ideal p power n or the submodule p power n. Okay, now let's understand the right hand side. What do submodules of z look like? So recall submodules of z are really the ideals or the left ideals of z. So what is a typical submodule? Well, z, remember, is a PID, therefore all ideals are singly generated. So the submodules of z are exactly the ideals generated by just a single integer d. Okay, so any submodule looks like this, and we want to know when does this submodule contain the submodule p power n. Okay. Now containment is again very easy to figure out for ideals in Z, as we have seen before. So if I have an ideal A, it contains B, that's the same as saying that one of them divides the other, right? So which divides which? Well, if A contains B, then A divides B. Okay, so this is for integers A and B. Okay, so what does that mean? So in our case, therefore I should say, so I had D contains p power n, means that D has to divide p power n. And we assume that, well, p is a prime, and so if I have a prime power, therefore a divisor of a prime power has very few choices really. What can it look like? It's again a prime power, p power m, where the power m is a number between 0 and n. Okay, so we have already understood quite a bit what are the submodules of z modulo p to the n. They are just the submodules. So on this side it's z modulo p to the n. The submodules are exactly submodules of the form p power m. You know, they are in bijection, if you wish, with submodules of the form p power n. Okay, so let's just write down that final conclusion. So the submodules of z modulo p power n are therefore exactly, what are they? They are all the submodules, they are the following form. So take p power m and look at its quotient. Okay, where m, so what is this? Another notation for this is what we used earlier, pi of p power m. Okay, where pi is the projection map from z to so all cosets of all elements coming from p power m, and m is now a number between 0 and n. So the submodules look exactly like this. Okay, now here's the interesting observation. These submodules actually form sort of a chain, okay, with one contained in the other. Okay, so that's the interesting thing with just having prime powers. So the key observation here, observe that if I look at, you know, what do the submodules look like, I can look at pi of p power 0. So as p power 0 by p power n, or p power 1 by p power n, all the way till p power n by p power n. Okay, this is just the trivial submodule of the quotient, if you wish, and they're all contained one in the other in this way. This is the largest, this contains the next guy, this contains the next guy, and so on. So on this side is the 0 submodule, and on this side this is the whole. P power 0 is just z, so this is z mod p power n. Okay, so observe that all the submodules behave in the following way. Okay, the quotient module z mod pn has the 0 module and the full module. They are of course submodules, but every other submodule occurs as part of a chain which goes from the bottom to the top. Okay, in particular what it says is that these b1s and b2s that I am looking for, right? So I'm trying to say, can I write this as some b1 directs some b2? Well, b1 and b2 but must both occur somewhere in this chain, right? If I could write it as b1 and b2, b1 must be one of them, b2 must be, you know, another, both occurring inside this chain. But observe, that will mean that either b1 is contained in b2 or b2 is contained in b1, right? They both occur as part of this chain somewhere. So if b1 and b2 are any two non-zero submodules, if b1, b2 are non-zero submodules, the observation now is that of z mod p to the n then the observation is that either b1 is inside b2 or b2 is inside b1. Okay, in particular it means that their intersection is not 0, because the intersection is one of them, it's either b1 or b2, whichever is smaller. right? And I have assumed I have two non-zero submodules. So what does that mean? It means that these two guys are not independent, in the sense that remember, to say that the whole thing is a direct sum of these two, what I need is that their intersection must be 0, right? And their sum must give me the whole module. Now in this case, the intersection itself is not 0. Okay, so this automatically proves that my whole module is definitely not, it doesn't make sense to say that it's their internal direct sum at all. Okay, so I mean, this is again, it demonstrates the utility of trying to understand submodules of a quotient in terms of modules of the ambient module.